Hello, class. We will now take a look at esters, which are carboxylic acid derivatives, and look at how to name them. So here's an ester. What we need to figure out is it is derived from a carboxylic acid. What carboxylic acid? So you can see the carbonyl carbon and then the oxygen that's directly attached to it. That's what you're looking for. So you take that guy right there. And then you draw that. I draw it to my left. So what is the name of this molecule? Well, that's acetic acid. So when we go from this carboxylic acid to an ester, what do we do? Well, what we're going to change is the ic acid. We're going to replace that with the word ate. So this piece right here in the pink box comes from this. So we could say acetate. See how I replaced the ic acid with ate. But now we also have this piece that we have to account for. And we can see that is a ethyl group. So we just have to stick that at the very beginning. So this molecule right here is called ethyl acetate. Now let's say we take a molecule that has two esters attached to it. How would we name that guy? Okay, now we have two esters. So we figure, okay, well, what would our dicarboxylic acid look like? So we would just take these ethyl groups and just replace them with a hydrogen. Like that. So what we're doing is we are taking this piece right here. Now what's the name of this molecule? And that one has a common name. That's malonic acid. So the same thing goes here, is we trade the ic acid for ate. So we could say malonate. But then we have our ethyl groups here that we have to take into account. And since there's two of them, we would just say di for two. And what are they? They're ethyl groups. So we have this molecule right here would be called diethyl malonate. Now we can have esters on rings, and we can also have esters in the rings. So we're going to take a look at those two different types. Okay. So let's take a look at that. Well, here we have another ester. So how do we name it? Well, we circle off that piece and we redraw it as the carboxylic acid derivative. What's the name of that carboxylic acid derivative? Well, we see that the parent name is going to be, well, we name when the carboxylic acid is on the ring, we would go cyclo for the 6-membered ring, hexane, we keep the E, and then we say carboxylic acid. Cyclohexane carboxylic acid. Now, I wrote that these two words need to be together, so let me rewrite that. Okay. Now, what we're going to do now to go to the ester, we are going to change. Let's see here. What's the better way of showing this? Your textbook shows it one way. So it's going to take this and that word, okay, and change it to this. Like that, carboxylate. So when we want to name this molecule right here, we would say, okay, this piece in the pink rectangle here is going to be, let's give ourselves some room here, cyclohexane carboxylate. So that accounts for that. But now what about that methyl group? Well, we have to specify that there's going to be a methyl. So the name of this ester right here is going to be called methyl cyclohexane carboxylate. To recall, if we have a molecule that looks like this, it's an O, like that. What is its general name? When you have an ester inside a ring, that would be called a lactone. Remember that? So at this point, that's all I want you to know about lactones. We don't need to necessarily know how to name them quite yet. So we won't go down that path, but if I decide to change my mind, we will talk about it in class if we want to start naming lactones. Now let's look at amides and how to name amides. We're following the same process as before. The amides are carboxylic acid derivatives. So let's draw the carboxylic acid that this guy would have been derived from. So how do I do that? I just replace the nitrogen with the OH. So what do we name this? Well, that would be acetic acid once again. And when we are naming acids, what are we going to replace? We're going to replace the ic acid and replace it with amide. So the name of this guy is simply going to be ACET. Replace the ic acid with amide. So what do we have here? Acetamide. But let's say we have something that looks like this. something like that. Well, we do the same process. What is its carboxylic acid derivative? What's the name of that guy? That would be benzoic acid. Now, when we have ic or oik, we're going to replace the oik also with amide. So the name of this amide right here we called benzamide. Now I want you to contrast that. Let's see here. Yes, I want you to see things are there's such subtle differences when it comes to nomenclature. So if we take a look at something that we've already seen before, acid chlorides, for example. Remember looking at this molecule right here? What was the name of that guy? Well, let's go back. What is its carboxylic acid derivative? There it is. It's benzoic acid again. But when we're dealing with acid chlorides, what do? We only replace the ic acid. And what would we replace it with? Il chloride. Not a dash. Or in this part right here would be any halogen, whatever the halogen is right there. And in this case, it's a chlorine, so we use chloride. If there was a bromine, it would be bromide. So the name of this molecule would be benzoyl chloride. Benzyl chloride. You see just the subtle differences here? In this one, we keep the O, and in this one, we get rid of it. Okay. So let's see. We can have amides on the outside of the ring, which we did that. Okay. How would you name this molecule if it was not a benzene? What if it was just a cyclohexane? What do you think about that? How would we name that one? Well, we would have to go back to its carboxylic acid derivative and name that guy. We would call this guy cyclohexane. Carboxylic acid. And what we're going to do now is replace the carboxylic acid part of the name with carboxamide. So the name of this guy right here, let's do it in green. The name of this molecule would be, and I'm going to write it a little below this, it would be cyclohexane. replace the carboxylic acid with that. Carboxamide. That's how you would name that species. Now, amides add another layer of complexity in which if you have alkyl groups attached to the nitrogen atom, what if these two hydrogens we replaced them with methyl groups? Or what if there was only one methyl group and one hydrogen? How would you name that type of species? So that's what we're going to look at next. So in this example, we see there's now a methyl group directly attached to this nitrogen atom. This is still an amide, but how do we name it? Well, the same idea here. We just look at this piece right here, okay? And we replace that nitrogen with what it was derived from by its carboxylic acid, OH. You see the blue box right here? So we have two carbons. We replace the nitrogen with the OH. And what is the name of this guy? Acetic acid. So if we go to this, what have we learned about amides? We replace the ic acid with amide, right? So we could call this part right here, we could call it acetamide, like that. But what's different with this problem is that we have methyl groups. So we need to specify where that methyl group is. Is that methyl group attached to the parent chain? No, it's attached to a nitrogen. So the way you do that is there's one methyl group. So you go N, and you're treating that N like a number. And whenever you have numbers and words, you always put a dash. So that N behaves as a number. So N-methyl. So the name of this molecule is one word, N-methyl acetamide. Now if we change this up a bit, what if I replace this hydrogen right here with another methyl? The same concept. You have this molecule, you go back to the carboxylic acid derivative, so it'd be acetamide, but now what's the difference? We've just tacked on another methyl group. So we have to treat it just like a number. So we have N, comma, N, because there's two groups on that N. How many are there? There's two, so we have to specify di. And what groups are they? They're methyl groups. And what's the parent? Acetamide. Just like that. Next, we are going to learn how to name nitriles. We'll do that next. Here we have is a nitrile. Now, we could expand this nitrile out to look like this. There, that carbon 1 is that carbon. And then that is connected to a triply bonded carbon. So that's carbon 2. So you need to be able to look at this guy right there and see this below it. So how do we name this nitrile? The same process as before. We have to go back to the carboxylic acid derivative. So we need to focus our attention on this piece right there. we see that there's 2 carbons, and then we will replace this triple bond nitrogen right here with an oxygen. So we would have our CH3 carbon double bonded OH. See, that's carbon 1 and that is carbon 2. And that piece right there, right here, comes from the pink over here. So how would we name this guy? Well, that has a common name of acetic acid. So what's the rule? Well, it's going to be the ic acid is now going to be taken off and going to be replaced with O nitrile. So how do we name this guy? Well, acetonitrile. Just like that. See how we replace the ic acid with O nitrile. Now what if we had let's say this guy? How would we name it? Well, we have to go like this. What's the carboxylic acid derivative? It would look like that. And we know that guy has a common name of benzoic acid. Now when we have the oic part, so this has the oic acid. We're going to replace the oic acid with the same thing, O nitrile. So we could say this guy's name, or this nitrile, is going to be benz. Add that O nitrile. Benzonitrile. Right. Now we have looked at many different types of carboxylic acid derivatives, and they're not all created the same. Some react really, really fast. Some react really slowly. And so what we're going to have is kind of a hierarchy of which ones are the most reactive and not. All right. So let's clean this off, and then we will start looking at the hierarchy of carboxylic acid derivatives and their reactivity. So here we have our carboxylic acid derivatives and our carboxylic acid. And they're ranked. The acid chloride is going to be the most reactive. And the carboxylate is going to be the least reactive. So you could technically draw an arrow showing reactivity like that. Another way you can look at this is like rungs on a ladder, that each one of these is a rung on a ladder. And as you go up, more reactive compounds are at the top. Now we need to understand why there's a difference in reactivity. So we're going to look at induction effects. We're going to look at resonance effects. Sterics plays a part in this. And we're going to look at the quality of the leaving group to help us explain why there's an order here. So the first thing that I want to take a look at is the leaving group ability. So let's draw another column here, kind of like down here. And I want to say in this column that we're making, what we're going to look at is the leaving group ability. So what leaves? Well, that leaves. So when we're doing a reaction with these carboxylic acid derivatives, what we're doing here is something like this. We're going to take our carboxylic acid derivative, and I'm going to represent that derivative with a Z. So this Z represents any of these. And what we're going to do is we are going to treat it with a nucleophile. And that nucleophile is going to then replace that Z. Like that, and then you are going to get the Z minus. So this Z right here is the leaving group. And how well does that leave? So we're going to look at each one of these leaving groups and take a look at that. So the acid chloride, when this Z group leaves, is going to leave and look like this. Negatively charged. Now let's take a look at each one of these. Okay. So what would the leaving group be for this guy? So that's the leaving group right there. And then that would be a leaving group. So we would have that right there. Okay, for the ester, the leaving group would be not that. It would be OR negative. So this one is for the ester. Then the carboxylic acid would be something like this. And then our amide, note that the R groups can be alkyl or hydrogen atoms. So the leaving group would be this guy, like that. And then the carboxylate would be an oxygen atom leaving as a 2 minus. Now when you take a look at the leaving group abilities here, we can make some, looking at the extremes, we can clearly see that a chloride atom is really large, so it has a lot of space for the electrons to delocalize and roam around. Whereas this guy, you never see an oxygen atom just leave. And then it's also -2, highly unstable. That doesn't leave. When you've been looking at SN2 reactions from Orgo1 and SN1 reactions, did we ever find an OH just leave? That's not a good leaving group. Neither are this OR, not a good leaving group. Now, we have this carboxylate type thing right here. It's relatively stable due to what? Resonance. So what we're observing here is the Z group. In each one of these, right here, these are our Z's. And the one reason why acid chlorides are the most reactive is because it has a really, really good leaving group. Now, when you take a look at these two right here, why do you think esters are more reactive than amides? Well, look at the leaving group. When you compare the oxygen to the nitrogen, which one's more electronegative? Well, it's the oxygen atom, right? So it can stabilize and handle that negative charge better than the nitrogen atoms can. So that explains why we see a difference in the reactivity for those two functional groups just based off of looking at their leaving group. But like I said, there's other factors that we need to look at when we're trying to explain the reactivity here. So we take a look at acid chlorides. What else do we have going on here? Well, we have a very electronegative atom. So what is that going to do? Well, that's going to pull electron density towards the more electronegative atom. And so as a result, what's going to happen is the carbonyl carbon right here is going to get partially positive. So let's just remind ourselves. Let's go back to our reaction coordinates here. What do? We have a negative nucleophile. And this is going to give us our nucleophile plus our Z minus. So remember also that reactivity has to do with an electron-rich species. So this is electron-rich. And we need an electron-poor region. And that is right there. Electron pores are also called electrophiles. So if we can make that carbonyl carbon more electron rich, then it's going to be more reactive with the electron. Maybe I misspoke. Let's start over. So we can make this carbonyl carbon more reactive if we can make it electron poor. And when it's more electron poor, then it can be more attracted to the electron-rich species. So in using inductive effects, we can see that this electronegative atom is pulling electron density away from the carbonyl carbon, making it more partially positive, which makes it more reactive. But when you contrast that with, let's say a amide, what do we have going on here? You have a resonance structure here with this amide that looks like this. Now look at that carbonyl. It doesn't look very electron poor compared to the acid chloride because the amide has some resonance. Now you might be saying, well, doesn't the chlorine atom, doesn't that have a resonance structure? Well, yeah, it does. We could, in theory, have a resonance structure that looks like this. Yeah, we could. But it doesn't contribute to the hybrid as much. Why? Because this atom's so electronegative. It's not going to want to donate a lone pair in to form this double bond. It just doesn't want to. And it doesn't do it as much as, say, the amide nitrogen. So the reason why this carbonyl carbon is electron poor is due to inductive effects. Now, if we take a look at amides, what do we have going on here? we look at an amide, so the amides are one of the least reactive of the carboxylic acid derivatives. Now, why is that the case? Well, let's compare it to acid chlorides, and let's even look at esters. So we can use the inductive, the principles of induction to help us explain the reactivity. So we can see that the chlorine atom is the most electronegative amongst these three. So it's going to pull electron density the strongest. And so because of induction, we are going to get the largest partial positive at that carbonyl-carbon. Now, when you compare nitrogen and oxygen, which one's more electronegative? The oxygen is more electronegative. So it's going to inductively pull electron density, and we're going to have a partial positive charge on that carbonyl-carbon. Nitrogen is the least electronegative, so it is going to pull electron density via induction the least. Do you see how I'm trying to show you different scales of that partial positive? So inductive effects are stronger for everything above amides because the nitrogen atom isn't very electronegative. And then you can look at resonance structures. Let's not look at it inductively. Let's look at it via resonance here. When we compare, let's say, the oxygen or the ester to the amide. And we've seen this before. Which lone pair is going to donate in more? So if we look at the resonance structures, we are looking at, note that would be a positive charge. O minus. R2, positive charge, O minus. So which lone pair will donate in more strongly? Well, it's going to have to be the nitrogen is going to donate in more because lesser electronegative atom. So its lone pair is going to donate in more than the oxygen atom, which when you look at the resonance structure, you can see that that carbonyl-carbon is not very electrophilic in comparison to this guy. So this carbonyl-carbon right there is going to be more electrophilic because this resonance structure right here contributes less than that guy. Pretty cool stuff, isn't it? One thing that we need to make sure we understand is the difference between the reactivity between a aldehyde or ketone and a carboxylic acid derivative. So if we take a look at a carboxylic acid derivative, we've seen this now a lot. We have our Z, and then we have our negative nucleophile, and that's going to replace the Z with our nucleophile, right? That's for carboxylic acid derivatives. But if you have, let's say, a aldehyde or a ketone, like this, and you try to do additive nucleophile, you are not going to get that. That reaction right here in green does not happen. Why? Are alkyl groups good leaving groups? Let's draw like this. Could you add, let's just say, an OH minus right here? Can you get this reaction to go? Is a methyl group a good leaving group? Does not work. So that's one of the major differences between a carboxylic acid derivative and a ketone or aldehyde. It's the leaving group ability. So what do we need to cover next here? So this whole process where you're taking a group and replacing it with a nucleophile, we call that nucleophilic. I probably misspelled that. No, I think I got it. Acyl substitution. So this name right here, nucleophilic acyl substitution, goes for that reaction scheme in blue right here. That's a name for that process. Okay. Remember, acyl groups are right here. So those are all acyl groups right there. Okay. Now we're going to proceed and learn a lot of reactions. And may I suggest, spend your time looking at the reaction mechanisms and knowing those like the back of your hand, because those will help you remember and learn reactions. So I want to kind of do a general mechanism with you, and that general mechanism will apply to most of these. Now there's going to be subtle nuances that are going to be, there's going to be some differences, but when you look at it big picture, the mechanisms are very, very similar. And that's what I want to show you next. Let's take a look at the generic form here. Here's our carboxylic acid derivative. We're going to treat it with a nucleophile, negatively charged. That's going to give us this. So how does it do this? Well, we see that we have a electron-rich species. And where's our electron poor? Well, remember that this guy has a resonance structure that looks like this. All right. So our electron poor species is the carbonyl carbon. So you can take this and then attack the carbonyl. So that's going to give us what? So we'll go and do the arrow down this way. So that will give us this compound right here. And I'm going to draw in the carbon now. And then we have our nucleophile, and then our Z right there. So this right here is very, very important because this is called a tetrahedral intermediate. So when you get to this stage of this tetrahedral intermediate, we have an oxygen atom that's negatively charged, and it's going to want its electrons here want to come back down. And when they come back down, the tetrahedral intermediate is going to collapse. And if I only leave that one pink arrow there, what have I made? I will have made a Texas carbon. So something has to leave. And when you compare your nucleophile and the Z group is typically, not always, but typically is going to be the better leaving group. And so that guy is going to leave. So then you will get your product that looks like this. And our Z is going to have that lone pair from those two electrons right there, and that will give it a negative charge. That right there is the general mechanism here. Now I want to show you an example or a specific example to get this point, get it home, or making sure you understand it. Okay, so that's the generic mechanism. Let's do an example. Let's say if we have something that looks like this. Okay. We have our, our acid chloride, and let's say we want to treat it with CH3, our methoxide group. Now, what's the mechanism here? Well, electron rich, electron poor. So we can go and attack just like that. Bring those electrons up there. So that's going to give us negatively charged, and then our OCH3. That right there is our tetrahedral intermediate. So when this guy comes and collapses back down, we have a chloride or the OCH3. Which one is the better leaving group? The chloride. So the chloride is going to leave like this to give us that. So what have we done? We have made a ester. So how can you make an ester? Well, get an acid chloride, treat it with a strong nucleophile, boom, you get an ester. Now, what you have to be very cautious about is this is not an SN2 mechanism. So many students will pretend that it's a SN2 mechanism and do a mechanism that looks like what I'm going to draw next. And this, what I'm drawing next, is 100% incorrect. And it does not work this way. Many students will be like, boom, boom, to give us so this is the interesting thing. If I gave you these two reagents and say predict the product, boom, that's the correct product. But if I say take these two reagents and show me the mechanism on how it comes to the product, this is completely wrong. This is showing us like an SN2 type thing. It's not an SN2. It is a nucleophilic acyl substitution mechanism. Don't make that mistake. So I know we're close to out of time, but I do want to make one more. I want to make one more point. All right. Now there, you will see mechanisms, something like this. Instead of using a methoxide, what if you used methanol? Like this. All right. So the product is still going to be the same. We form an ester. But do you see how this piece right here came from this piece right there? What does this piece not have that this piece does have? You can clearly see that you still have a hydrogen atom. So when you do the mechanism here, there's going to be a proton transfer that you have to take into account. So if I redraw our methanol here, mechanistically, what's going to happen? Boom, boom. And so that's going to give us our tetrahedral intermediate. And we have a positive charge there. Okay. Then we can have a proton transfer where a second methanol molecule can act as a base to deprotonate that hydrogen. Then we will get O minus, OCH3. And then the lone pairs on this oxygen can come and collapse down, kicking off our leaving group. Like that. So if you go back to the general mechanism for nucleophilic acyl substitutions, you will notice that I didn't show you a proton transfer. But proton transfers are the most simple, basic, elementary step in organic mechanisms. Okay, we will continue our discussion about all these reactions in the next video.